well, fundamental, light.
Absolutely. It's everywhere.
Right. We flick a switch, light fills the room, phones, screens light, creating entire worlds. But how much control do we actually have over it? Something so fleeting.
That's a great question. And it's evolved, hasn't it?
Hmm.
Historically, our control was, big scale, like giant telescope lenses, huge mirrors.
Grand gesture.
Exactly. But now we're talking microscopic, even nanoscopic control. This whole journey leads us into nanophotonics.
Nanophotonics, okay.
Yeah, where we engineer how light and matter interact at scales smaller than the light's own wavelength. Gets really interesting there.
So that's our mission for this deep dive then. Understand optical confinement, how we get light to stay put, basically.
Precisely. Where we want it, when we want it.
And you're saying this isn't just tech wizardry. It connects to, well, fundamental physics, space-time.
It really does. Localizing photons has some profound implications. It bridges classical ideas with the quantum world.
Okay, I'm intrigued. Expecting some aha moments, definitely.
Hopefully.
Let's unpack this then. Starting with the basics, maybe the most intuitive thing, just directing light, getting it to go where we want, maybe around corners. How do we do that without it just spilling everywhere?
Right. So the main workhorse for guiding light, especially in materials like glass or plastic, is total internal reflection, TIR.
TR, okay.
Imagine like a pipe for light.
Yeah.
An optical waveguide. It has a central part, the core, and it's surrounded by cladding.
Core and cladding, got it.
The key is the core is slightly denser, optically higher refractive index than the cladding.
Okay.
So Snell's law tells us that if light traveling in that denser core hits the boundary with the less dense cladding at a shallow enough angle.
Shallow enough meaning quite parallel to the boundary.
Exactly. Greater than a specific critical angle. If it hits like that, it doesn't pass through. It reflects. It reflects.
Completely. Bounces back inside.
Perfectly, like hitting an invisible mirror. So it bounces down the core. Effectively trapped.
So it's like a super precise pinball game inside the material.
Kind of, yeah. But the bumpers are just the boundary between the two materials. Keeps the light contained.
And that's the idea behind optical fibers, right? The internet's backbone.
Exactly that. Miles and miles of fiber guiding light pulses using TIR. It's what connects the world, really.
Wow. Just based on that simple principle.
Simple, but powerful. And it's not just those massive cables. The same physics works in tiny waveguides on photonic integrated circuits, PICs.
So chips that use light instead of electricity.
Basically, yes. Often made from silicon, glass, using, lithography techniques like making computer chips.
Yeah, I see.
And while TIR in these dielectric materials is super common, you can guide light other ways too. Metallic surfaces can do it, or even more complex things like photonic crystals. We can get to those.
Okay, interesting. So we can steer light, but guiding implies it's always, well, moving. What if we want to stop it? Like, truly hold it in place?
Ah, yes. Trapping light, not just guiding it along a path.
Is that even possible?
Yeah.
Light seems so inherently mobile.
It absolutely is. That's the job of optical cavities, or you might hear them called resonators.
Cavities.
They can find light in a specific location, both in space and in time. The simplest way to picture one, just two mirrors facing each other. Highly reflective mirrors.
Like in a laser.
Exactly, like in a laser. That's a classic example. Light bounces back and forth. But here's the twist. Light's a wave.
Right.
So only certain wavelengths, specific frequencies, can actually fit perfectly between the mirrors. They have to form a stable standing wave pattern, like plucking a guitar string. Only certain notes resonate.
Ah, so other wavelengths just kind of cancel themselves out.
Pretty much, yeah.
Yeah.
Destructive interference suppresses them. Only the resonant modes survive and build up intensity inside the cavity.
Okay, so how do we know how good a cavity is, how well it traps the light?
We use two main figures of merit. First is the quality factor, the Q factor. It basically tells you how long the light hangs around in the cavity before leaking out or getting absorbed. It's about temporal confinement. Think of it as energy stored versus energy lost per cycle.
So a high Q means light stays trapped for a long time, low loss.
Exactly. A very long photon lifetime, which also means the resonance is very sharp. The cavity is very picky about which frequency it traps. High frequency selectivity.
Okay, Q factor for time. What's the second thing?
The second is the mode volume, usually written VEF. This tells you about spatial confinement.
How small a space it's squeezed into.
Precisely. It's the effective volume the light mode occupies. A smaller VEF means you've pack the light energy into a really tiny region.
Making it very intense in that spot.
Incredibly intense, yes. High field intensity.
So you've got the Q factor keeping light trapped for a long time, and the mode volume squeezing it into a tiny space. Why are both important together? What's the magic when you combine them?
That's where things get really powerful for light-matter interaction. When you have both a high Q and a small VEF. Any interaction between the trapped light and something placed inside the cavity, say an atom or a tiny semiconductor quantum dot, gets massively boosted.
Boosted how?
The rate of interaction goes way up. There's actually a term for it, the Purcell factor, FP. It scales proportionally to Q divided by VEF.
Ah, so Q over V, that ratio is key.
It's fundamental. It's why lasers work so efficiently. It enhances their emission. And it's absolutely critical in quantum optics, quantum information. Anywhere, you need a single photon to strongly interact with a single quantum system.
Okay, that is remarkable. We've gone from guiding light to pinning it down and making it resonate powerfully. Can we push this even further, like engineer the actual material the light travels through to control it even more fundamentally?
Yes, absolutely. And that's where we get into photonic crystals.
Photonic crystals sounds cool.
They are. These aren't usually natural crystals. They're artificial structures we design and build. The key idea is a periodic variation in the refractive index.
Periodic meaning,
Yeah.
repeating pattern.
Exactly. A repeating pattern of high and low refractive index on a scale similar to the wavelength of light we're interested in. Think of it like building a crystal lattice, like in silicon, but designed for photons, not electrons.
Okay. What does that structure do to light?
It creates something called the photonic band structure. It's analogous to the electronic band structure in solids, which determines how electrons behave.
Right, like conductors, insulators, semiconductors.
Precisely. The photonic band structure tells photons which energy levels or frequencies are allowed or forbidden within the crystal.
Forbidden frequencies, light just can't exist at those frequencies inside the material.
That's the core concept. It can lead to a photonic band gap, a range of frequencies where light simply cannot propagate through the crystal in any direction.
Whoa, so for those frequencies, the crystal is like a perfect mirror, no matter the angle.
Effectively, yes, an omnidirectional mirror within that frequency band. It's completely opaque to that light.
Okay, so how do we use this band gap to trap light then, if it can't even get in?
We introduce a defect. We break the perfect periodicity intentionally.
A deliberate flaw.
Exactly. Maybe we remove one tiny feature like an air hole in a repeating pattern, or change the size of just one element. This defect creates a localized spot where light can exist, even if its frequency is within the band gap of the surrounding crystal.
So light gets trapped right there at the defect.
Precisely. The surrounding perfect crystal acts like an impenetrable cage because of its band gap. Light at that frequency literally has nowhere else to go.
And this gives you good confinement.
Phenomenal confinement. You can get ultra-high Q factors and incredibly small mode volumes this way. And importantly, without needing traditional mirrors. The crystal structure itself forms the cavity. That's huge for making tiny lasers and complex circuits on chips.
That's a real paradigm shift.
Right. It is. Think about the progression. TIR tells light which path to follow. Resonators use interference to select specific wave patterns along that path, trapping in time. But photonic crystals, they operate more deeply. They engineer the actual medium to dictate whether a photon of a certain frequency can even exist there.
You're manipulating the fundamental possibilities for light.
In a way, yes. We're controlling what's called the local density of photonic states, the LDOS. It's like changing the available slots for light at a specific point in space. It really connects classical optics to quantum electrodynamics, QED.
Amazing. Okay, this leads to another point. For ages, there was this idea of a fundamental limit, right? How small you could focus light. You couldn't see things smaller than a certain size, the diffraction limit.
Ah, yes, the classical diffraction limit, described by Ernst Abbe way back.
What was the basic idea?
It essentially said you can't focus light down to a spot significantly smaller than about half its wavelength, lambda over 2.
So for visible light, maybe a few hundred nanometers.
Roughly, yes. Maybe 250 nanometers or so. The limit arises because fine subwave-length details about an object are carried by what we call evanescent waves.
Evanescent wave.
Yeah, these are non-propagating waves. They exist very close to the surface of an object but decay extremely rapidly, exponentially, with distance. In conventional microscopes, that information is just lost. You're too far away.
So you just couldn't resolve anything smaller than that E2 limit using traditional lenses?
That was the conventional wisdom for a long, long time.
The source material says this limit has been shattered. How? How did we get around such a seemingly hard physical rule?
That's been one of the really exciting frontiers. Fields like near-field optics and especially plasmonic.
Cosmonics.
Right. These fields developed ways to interact with those evanescent waves directly before they decay away. They allow us to confine and manipulate light on scales much, much smaller than the wavelength, deeply subwavelength, nanometer scale.
How does that work in practice? Any examples?
A key technique is near-field scanning optical microscopy, NSOM.
NSO.
In NSOM, you essentially force light through a tiny, tiny hole at the end of a sharpened optical fiber probe. A hole much smaller than the wavelength.
Like a nanoflashlight.
Kind of. It creates a subwavelength light source right at the tip, which you scan very close to the sample surface. This lets you see or interact with features far smaller than the old diffraction limit would allow. You're essentially collecting that evanescent information.
Incredible. We've really covered some ground today, from just steering light with TIR,
To trapping it in cavities with high Q and small v.
then engineering the material itself with photonic crystals to forbid or allow light.
And finally, smashing that old diffraction limit to work with light at the nanoscale using near-field techniques.
It's an amazing progression of control.
It really is. And connecting back, these aren't just isolated tricks for technology. Gaining this level of control over photons, designing their environment, it's giving us tools to probe the very nature of light itself, its relativistic properties, its quantum electrodynamic behavior. It might even offer ways to explore fundamental questions about space-time structure, potentially.
So manipulating light helps us understand the universe's fabric.
That's the hope, and the direction some research is taking. It links practical optics back to fundamental physics in really deep ways.
So looking ahead, with these incredibly precise tools for controlling light, what frontiers might open up? What does this level of manipulation unlock, not just for tech, but maybe for our basic understanding? What really stands out to you about how controlling light changes everything?